Welcome to this session. And this session we give the definition of residue of a function at a pole. So let z equals to a. Be a pole of order m. Of a function f of z and C1 be a circle of radius r units with center at the point z equals to a, which does not contain any other singularities except z equals to a So let that be the thing. So let a be the pole of order m of a function f of z, and we define C1 to be a circle of radius r centered at this point z equals to a, which does not contain any other singularities except the point z equals to a. Then f of z is analytic within this annulus r less than z minus a less than capital R, and can be expanded within the annulus. So let's draw a diagram to illustrate that. So we have this circle, C1, and then we have this a point A, and then we have another circle, bigger circle of radius capital R. So this is C1, this is C2. So this is R, while the radius of this one is small r. So this is the annulus region between these two circles, C1 and C2. So what I've shaded is the annulus defined by the two circles of radius capital R and small r. So this shaded part is the annulus. By Lorentz series, So we have f of z is given by summation n from 0 to infinity of a sub n z minus a power n plus summation n from 1 to infinity b sub n z minus a raised power minus n. So let's call this Lorentz series about the point z equals to a, call it equation 1, where from definition a n is 1 over 2 pi I integral along c f of z divided by z minus a power n plus 1 dz. Let's call this one 2, and bn is 1 over 2 pi I integral along c1 f of z over z minus a raised power minus n plus 1 dz. Let's call this one 3. So, and this circle z minus a equals to r is the circle C1 we have defined in this integral in equation 3. So particularly, if we set if we let n to be 1, then 3 becomes b1 is equals to 1 over 2 pi I. So minus 1 plus 1 is 0. Z minus a raised power 0 is 1. So we just have the integral along C1 of f of z dz. So that's what we have. So now once you get the coefficient of b1, then that is what we call the residue of the function f of z about the pole or about the point z equals to a. So the coefficient of the coefficient, actually the coefficient b1 itself. So the coefficient b1 or the value b1 is called residue of f of z at the pole z equals to a. We denote it as or we denote it by mean residue at z equals to a is given by b1. So that's how we define residue of a function f of z about the point z equals to a or about the pole z equals to a. So in the next session, we give different methods of finding or calculating residues of functions. So please watch the next videos to illustrate different methods of finding residues of functions. Thank you.